Systems, and our presenter here is David McCauley. And just by way of introduction, David has retired from J. David McCauley Architects Incorporated, located in Guelph. He's a graduate of the University of Waterloo with undergraduate degrees in environmental studies and architecture. His practice was established in 1978, and David has since received a special designation as a building biologist and continues to consult for new construction and alterations, designing healthy, sustainable places. In his designs, he brings together learnings from building biology, the passive house, net zero, biogeometry, and biophilia. Having completed many innovative buildings throughout Ontario using sound building construction technology and proven building science, David continues to bring these techniques, design of long-term care, community buildings, multi-unit dwellings, schools, healthcare, workplaces, and wellness facilities. This company implemented many measures which have seen considerable reductions in electrical costs, water consumption, transportation, waste, and embodied energy, whilst reducing the impact on the environment, supporting healthy lifestyles, environmental sustainability, and energy efficiency. The firm's focus has included care and wellness facilities, as mentioned, and David has had many speaking engagements. Welcome, David.
Thanks, JJ. I'll just take it away, and I think Steve is going to be going through the slides for me, so appreciate that. And we can go to the next slide. So I just wanted to talk very briefly. I have quite a few slides here. I'm just going to touch on a lot of them, and I think they'll be available if you need further studies or examples. You can feel free to go through the slide deck. But first of all, we want to know why we want to consider the building envelope, and certainly some of those are reduce the consumption costs. But we're also looking at comfort, building durability, and there's been a lot of talk that I've heard today about HVAC equipment sizing and that type of thing, and that requires smaller equipment and less maintenance for that as well. So these are just some of the highlights. I'll go into more of that as I go through the presentation. Okay, next. Next slide.
There'll be a delay here, but yeah, I'll get it.
All right, so as far as the building envelope, the way I want to present this is, first of all, I want to go through the characteristics of what a building envelope requires. I want to go through the components, and you'll know what those are. And then I'll go through the implementation about how that can work or not work, and how we could undergo any changes to the building envelope to improve the efficiency. So next slide. Beginning with the characteristics, certainly we're looking at the characteristics as far as our environment in Canada is concerned, with water vapor, vapor retarder, air, thermal, water, and effective thermal insulation, and then of course water shedding. So we'll get into the characteristics then in the next slide. So air tightness, we talk about air tightness, and we're talking about the air infiltration through the building envelope all the way through, and we can certainly tighten up the building envelope and reduce the amount of air moving. As anybody knows, with insulation, you can usually blow right through it, so it needs to have air tightness in addition to the insulation. So we're looking at that on the air tightness as the exterior. As far as the air tightness is concerned, that could be anywhere in the envelope. Next slide. And certainly the characteristics for the air tightness are to minimize the airflow through the building systems, and loading dock doors, overhead doors, and certainly behavioral changes in many of these facilities as well. Next slide. So the way we do this, and this is a very low-hanging fruit as far as improvements is concerned, is to do weather stripping, sealing, smart air barriers, and that type of thing to tighten up the building envelope. And this is a regular ongoing maintenance for the building as well. Next slide. So the air barrier challenges are certainly in the areas where the materials and the components of a building intersect. So it's the leakage is usually where they join windows, doors, eaves, floor to walls, and in foundations and that type of thing. That's usually where you get the airtightness failures. Next slide. So in summary, it should be strong, stiff, continuous. You should be able to trace it around the whole building from the roof right down to the foundation and even underneath the foundation. Next slide. So we look at materials as far as hydroscopic materials as concerned that wick moisture. Some materials and some insulations particularly, and I'd have to say that fiberglass is one of the worst of those. Once it gets wet, it's basically toast as far as insulation is concerned. And moisture definitely affects the thermal resistance after wetting, as I say. Next slide. So we're looking for vent holes and of course flashings, that type of thing. To everybody's seen buildings like this where the windows are failing, and it's usually the moisture that's getting behind the windows and trapped in there that freezes and thaws and causes the spalling, that type of thing. So we want to make sure that's there and covered. Next slide. So again, the characteristics, hopefully none of your buildings look like these, but you can see some of these things in water penetration. I've shown a good brick example, but buildings, whatever they're made of, will have failures in some of these systems over a period of time. Next slide. So the way moisture works in buildings, it changes in our climate from summer to winter, so that you'll find condensation in the exterior of buildings in winter conditions, which cause frost and that. And then in the summer, it's the reverse, so you get condensation on the inside and the windows and things like that. So again, it's a reversing trend. So it requires careful location of moisture control. Certainly when we take buildings apart, we can see where the damage is done in behind some of these walls where it's had failure to control some of these things. Next slide. And you'll see examples here. EIFS is the exterior insulation foam system, is quite notorious for having leakage, as anybody knows. And careful air barriers have been introduced since that material became popular in Ontario, and certainly the leaky condos of BC. And this is typical of that type of thing. Next slide. And certainly in moisture control, we're looking at moisture in a lot of areas in buildings where it hasn't been handled with flashings and that type of thing. It's complicated buildings here. Okay, next slide. So thermal insulation, coming into that, it's very important to have continuous insulation and not breaks in it. You can find out where the leaks are with infrared cameras and drone exterior faces of buildings. Next slide. We want to take advantage anytime we can to put continuous insulation, as I've mentioned, and ability to repair, have access to it, and so it can be inspected. Next slide. So thermal bridging is where the components come together. In this particular case, it's a structural lintel over a window that's a direct contact to the exterior, and it'll cause corrosion there and leakage. It's actually not the window that's leaking, it's the moisture in the wall that doesn't have a path to the exterior. Next slide. And this is an example, again, of thermal bridging. There's conduit on the exterior in the EIFS system, and this is where it was leaking. It was because of these steel conduits that are in the thermal insulation and reducing the effectiveness. So this is a common thing as well. Next slide. So we're looking at durability as far as long-lasting construction. There are ways to do it with things like stainless steel ties. Most buildings now are designed to last anywhere from 30 to 50 years at the maximum. We probably won't have any heritage buildings after that period of time for the buildings we're building today and the way we're putting them together. So next slide. So we're also looking at the full energy and 100-year buildings. It actually costs a lot less in terms of the lifestyle of the building. but we're also looking at careful design. And this particular building that we were asked to retrofit, the sections and the details didn't show this detail in 3D the way that I'm looking at them here. And the water comes down in this eave, so there's a valley here that drips right down. There's no eaves trough to protect it. Comes right down the flat fascia there and right onto the eaves. It wasn't designed to hold moisture, so it breaks down very rapidly. This is only after a few years. Next slide.
David, it's JJ.
Yep.
We have one question in the chat, and someone is asking, just for clarification, what is stainless steel ties?
Yeah, you'll know those as they call them helico ties. So they're kind of a spiral thing, and they fit into the mortar joints, and they're made of stainless steel, so they'll last 100 years easily. As opposed to, if anybody's taken buildings or seen them under construction with galvanized ties, they might last 25, 30 years, and then they corrode, so they're really not effective anymore, and that's why you see the brick failing from the wall structure behind it. I can get into more detail if that doesn't cover it, but you can find them. Just look up helical stainless steel ties, and you should be able to find them.
That's great. Much appreciated.
Another point of durability is the renovations and reuse of buildings. This is the Humber River Regional Hospital. We turned that into a temporary long-term care facility. This was a while ago, so long before COVID, but when we find buildings like this that are adaptive for reuse, this is one example of where buildings can find new life without going to a lot of construction. Next slide. And common failures, as you can see here, are bricks and mortar and that type of thing. And again, this is an older building, but the design of protrusions like this is a real issue. It's just asking for any kind of damage with water and sheet drainage and that type of thing to happen. And it can't be maintained. I think this is the 3rd or 4th floor, so it's not easy to get access to it. Next slide. So the components in terms of priority, water control, we talked about air control, thermal control, and then vapor control. So there's ideal locations for these, and I think the next slide shows that, JJ. So typically in the roof, about 20 to 30% of the heat loss is through the roof, and we have to consider drifting snow for that, and also PV arrays. That's going to be the subject of another talk. But when we're designing roofs now, we almost always consider enough structural design to carry roof panels for the future if they're not installed immediately. Next slide. So slope to drainage is another thing. Beware of the scuppers and eaves trough and that type of thing. They're always a maintenance thing, and they have to be inspected on a pretty regular basis because it can lead to the failure of a building just with a blocked rainwater leader and things like that. Next slide. We talked about snow drifting and that. I think are we going forward or backward here? We heard some talk about exhaust fumes and that type of thing in the intakes. That's another common thing. We have to be careful about mechanical design of those things. Next slide. So building roofs, a lot of people say, well, a dark roof is better, but actually not. Light colored or white colored membrane is better. You can go with a green roof for sure. That has longevity to it with some maintenance. An inverted or ballast roof, which prevents the UV rays from reaching the roofing membrane, has a much longer roof and requires a little more structure to carry it. But certainly these are some of the working roofs that are much more efficient than typical ones you see. Perfect Wall has, I don't want to get into the details of all this. This is kind of building science. But anyway, there are places for all of these membranes. We go to the next slide. So protrusions and penetrations, nice bump outs and that type of thing are always look good on architectural drawings, but they have a real problem, as you can see, with the amount of flashing and caulking here. It's hardly worth it. Okay, next slide. And as far as windows are concerned, another component in it, we have triple pane. You have to look at the orientation, overhangs, and reflective films. Next slide. So we look at operable windows where we can, allow for cleaning on the inside and adjustable colorings. Next slide. So insulated frames, we're looking at heavily insulated frames for high performance buildings and not just thermally broken. Next slide. We talk about weather stripping, especially at doors and operating windows. Inspect the caulking and adjust the closers, make sure that the leaks aren't there. Next slide. Other considerations, I just wanted to cover on these. I don't have slides to support this, but landscaping to shade the building, reduce the air conditioning, treed parking islands, consider the prevailing winds and drought tolerant native plants. And we talked about biophilia a little bit. I can touch on that. Next slide. So we're also looking at integrated systems and holistic design. Get the mechanical engineers talking to the structural and the architectural, the interior designers. Look at occupancy sensors. Another good book that applies to a lot of this is Checklist Manifesto by Ato Gawande. Highly recommended it. It's a learning exercise for anybody. But anyway, I highly recommend it. Next slide. So implementation and how it looks. Again, what are the building options? What are the options as far as the building is concerned? So next slide. Basically, this is do nothing, do minor repairs, or do longer, more extensive repairs. And certainly looking at return on investment and life cycle payback. Possibly leased. You can lease most equipment and even building components, and certainly a PV roof lease we'll probably get into in the next presentation. Next slide. Financial, actually there's very little cost in adding insulation and higher performance windows and caulking and things like that. There's a lot of savings to be had through heating bills and that type of thing, and no cost for good design of thermal bridging and that type of thing. Just careful design at the earlier stage. Next slide. So you can also look at government programs, partnerships, funding for retrofits, and certainly endorsements if you can get those for the use of some of the products. And some of this is really good. And a lot of new products are becoming available in the last even 5 years that are available that weren't available in this country at that time. Next slide.
So David, we're really good on time. So we've got some good implementation stuff here, so you can definitely spend a bit of time on it. So.
Yeah. Okay. I'll go through this case study. A case study for the Weeneebayko General Hospital. This is not my project. I've got the information, and so they've replaced their windows on General Hospital up north. And next slide, we can go to that one, and showing some of the examples of their windows, their operating windows. And what they looked at was the cost for the window replacement and door replacement of $1.4 million. The lifespan expectancy about 25 years, which is probably optimistic. The annual cost savings, $126,000, and the annual savings, that's annual. The lifetime saving about $3 million. So the return on investment about 9% without the incentives. I think there were some incentives that were given for that as well. So it's amazing how just replacing the windows. Windows is a fairly expensive replacement, as you can imagine, and it's troublesome as far as implementation is concerned. And I'll get into that in the next few slides about it's not low-hanging fruit, I guess I could say. So the next slide.
David, it's Michelle here. I got a quick question for you.
Yes.
Does the saving include the reduction in infiltration when you change windows?
Is that the reduction in infiltration?
Yeah, because you're going to improve the window R value, and you will reduce exfiltration, infiltration. Would the savings you showed include that component? Yes.
Yeah, it's obviously not just the windows. I was looking at a building last week, actually. The cost of infiltration is about 40% of your heat cost. So it's not just the insulation. Insulation is about 60%, I guess, if that's the remainder of it. But 40% is actually the infiltration of air through the building envelope. So that's a significant thing that can't be ignored. So certainly take advantage of when other things are happening, when you're re-roofing, certainly to increase the insulation. If you're redecorating the inside of the building, if you're providing new services and boilers or heating systems, that type of thing. Certainly recladding, especially if you can reclad and put the insulation on the exterior. If you're going through a change of use in a building or a portion of a building, that's an opportunity to, again, to include energy retrofits in that building program and see the payback for that, and certainly repurposing of some areas. Barrier-free accessibility, we're always upgrading barrier-free accessibility, and part of that as well can be energy upgrades of insulation or electrical systems. I mean, there's a lot to learn, and I'm not the expert in control systems, but there's leaps and bounds in terms of occupancy sensors and things like that as far as lighting is concerned. Certainly relamping and relighting fixtures and that type of thing, again, are opportunities for savings. So next slide. Okay, and the other thing is to do an audit. So I talked about infrared cameras, and you can see the one on the left and the right on this bottom slide of this apartment building is, and this is the imaging that they had before on the left and after on the right. You can see where the heat loss is in the windows, but the difference is, as I say here, night and day. Certainly drones and that type of thing, and inspecting roof and ceiling leaks and that type of thing on an ongoing basis, and look for moisture in basements and that too. It's not necessarily a roof leaking. I don't know how many times I've been called out because the roof is leaking, and it's not at all the roof leaking. It might be moisture, hot air escaping somewhere into the building envelope in the ceiling, and it's nothing to do with the roof at all. Roof membrane. Next slide.
David.
Yep.
David, it's JJ. I just, when you talk about the infrared cameras and drone surveys, you know, this is fairly new technology. It's out there, but I just wonder if you have any tips on what to look for in a good service provider when it comes to that sort of.
Yeah, it's not a new technology by any means. I think it came into the Second World War quite readily with the munitions and that, but it's readily handy. What I do is go to the Sustainable Builders. So I have connections with the Natural Building Coalition in Ontario, and you might think they're a bunch of hippies doing straw bale houses and that type of thing, but they have a lot of knowledge as far as building envelope is concerned. So they almost always have infrared cameras. Certainly people who do audits, building audits, and even testing, house testing and things like that for house inspection reports, they often have infrared cameras, and you can certainly rent them at different. I'm not sure Home Depot has them, but certainly they're out there for rent. And you know, if you don't want to buy one, they're not that expensive anymore anyway. So a good larger corporation or school board certainly would have them. Blower door testing, again, the same thing could be said for those. I mean, they're pretty common. Mm-hmm. They're not as into larger buildings, but there are ways of measuring this. Basically, they pressurize the building and they measure where the air leakage is, and you can actually see it, or you can use a smoke pen to find out where the leaks are. And I just had a friend do his house that way, and I think it basically they're coming back after they've done all the caulking and round windows and things like that, and before the finishes go back on again, they're retesting it to make sure that the improvements they've made are fully effective. So it's a matter of testing and then retesting again as well. Next slide.
You can do that, David, on large buildings as you're showing here. I know one of my colleagues did it on a 12-story building. It was like a residential building, but it can be done on large buildings, and I think it is effective.
Yeah, and it's a little more sophisticated for a larger building than a house sort of thing, but it's a very simple. I mean, these things are available, and again, you can rent them too. So as far as certification is concerned, for implementation, you can look at code compliant, which is kind of the base level. You can look at LEED. LEED is becoming a little passe in a lot of ways that I see now. So net zero, Energy Star, passive buildings are basically exceeding the requirements of all the others. Next slide. As far as documentation, be sure that you have your as-built drawings and specs, and ask for those for any projects you're doing. Ask for as-built drawings and specifications, shop drawings. You can look at the performance criteria for the systems I talked about. You can look at similar buildings and upgrades that they've done, and networking is really important when you get into this, and that's what conferences like this are about. Next slide. Next slide.
Just gonna read a question here as I change the slides.
No, go ahead.
Slightly different topic, but does anyone have any experience using exterior window shading systems to reduce chiller energy consumption? See, there was a question put out there. David, have you run into any?
I haven't seen it directly. It's hard to document a lot of these things. Later on, I'll show you. RDH is a company that does building forensics with building envelopes, and they have a lot of studies. They're out of the University of Waterloo, basically a lot of people from that. They would have the stats and the credible evidence to present to people if you're looking at improving projects. So window shading is something, but also in modeling buildings now, before we go through the process, basically even permitting buildings nowadays, we're energy modeling buildings, and shading of the windows and orientation of the windows is certainly one of the things that's considered in that. But that's no reason to say that you can't take an existing building and energy model that and see the effectiveness of window shading for.
I've done, David, it's Michel here. I've done a lot of modeling of window shading. When it's passive shading that you add, you get a net cost benefit, but you get a net energy penalty in most of our climate because of the loss during the heating season.
Yep.
So Michel's saying that if folks couldn't hear that you get a net energy benefit, but then you get a net energy impact during the heating system potentially as well. So you have to be really careful in those situations.
Yeah, and there's a correct overhang that you can calculate as well with again modeling, because you can model it summer and winter, and you can see the sweet spot where you're getting the heat gain in the winter and the heat shading in the summer. So or you can get louvers. Louvers will do it, and they don't have the structural implications either of a solid and a roofing type material that would be a shading device. Those can be built into certainly the design of the building, but you'll see a lot of louvered ones on buildings, especially with south-facing windows. So as far as
David, while we're on the topic of windows, it's JJ again. You're talking about insulated and thermal-broke window frames. Is there any preferred window frame material? What would you look for to get the longest life expectancy out of a window system?
Yeah, the window. Okay, I'll tell you what not to use is, and I hope if anybody's here, I can prepare to get into the argument. Vinyl windows are probably the absolute worst. But as far as windows is concerned, I've been using Passive House windows in wood, and they have an exterior clad, usually aluminum or window frames, so it doesn't get the damage to the exterior, but it has about an inch of insulation, a high foam insulation on the exterior of the window frame. So the mistake is that people look at the glass itself and put in triple glazed glass and argon filled and coated and that type of thing. And basically the loss, you get about 20% of the losses in the window frame itself, depending on the size of the window. But if you look at the window itself and you actually do the calculations for most windows, it's about 20% is the heat loss through the frames. And the insulated frames, the thermally broken insulated frames might be an R2 or something like that, where you're looking at a wall system that's probably at least an R20 or R50, if we can get up there. So where you're getting, that's why you get condensation on the inside of windows. And whether they're wood windows, people say, well, wood windows don't last. Well, I'm living in a house with 135-year-old windows. They're original windows. They're wood inside through to the outside. Wood does last. It's a question of how it's installed and protected. So the material is not the most important thing. We've been looking at fiberglass. Aluminum is a very good conductor of cold and heat. So it's good to avoid that if you can. That's why we prefer fiberglass or wood windows, because it doesn't condensate in the same way. But again, the important thing is to insulate the exterior of the windows, actually.
Thank you.
Okay, so getting into the expertise, certainly building science people, materials testing, designated substances reports and roofing people, engineers and architects, a lot of those out there with expertise or without expertise. There's certainly building envelope scientists as well. I also like to bring in the occupational health people because they can talk about what, especially today, what how the building affects people's health. And with my study of building biology, and there's a number of other people around who do consulting on that. It's not just looking for mold; it's looking for a lot of other contaminants that are in the air. I'm not going to get into the subject. I just want to talk about electromagnetic radiation as also one of those. And in a lot of the buildings we're looking at now, especially with Wi-Fi and a lot of high energy cell phones and things like that, high frequency radiation, that's definitely a health factor in buildings for people who are sensitive to those things. But
David, we have another chat question. Excuse me for breaking in.
Okay.
We have someone asking, any opinion on the availability of sufficient labor force locally with needed skills to install and maintain net zero or passive technologies in buildings? And I know there's a few people that run into those issues.
Yeah, and you might be reading ahead of my slides because that is certainly one of the challenges in implementation is finding the right kind of contractors.
Right.
I think to some of the people who are more progressive in these things, and it's the home builders, basically institutional are coming on stream. But we've just had the first few passive house or passive buildings in Canada that are institutional buildings, and it's more difficult to get those people convinced. Contractors are interested in it. What I've seen in a number of projects, there's a couple of projects in Hamilton I know of where they had a partnership. That's where we talk about a collaborative team, really. It was a major commercial builder in Hamilton who came together with an experienced passive house builder basically, and they put their expertise together to build a number of apartment buildings, low-cost apartment buildings with that partnership. So it's a matter of training, and people are out there that certainly we're looking at a generation. People in the construction industry are, I don't want to fault them all because they're great people, but they don't necessarily keep up to date as far as their training is concerned or their methods, so they do have to be trained. So basically my suggestion would be to talk to the house builders who are doing net zero passive house buildings, and they have the expertise. We're having a hard time finding large enough builders to build long-term care and hospitals now that have that expertise or that interest, even as far as that's concerned. But it's a matter of training. That it is out there, and partnerships I think are great to go. Can we do the next slide? We'll get into some of this stuff too. So we talked about these expertise. As far as the design program is concerned, this is where I think a lot of these people come in. They're attending today is to get the right objectives and aims and the function. So write your performance criteria and put it into your specs when you go out there to contractors. And basically go out there looking at a longer term program and spend a lot more time in the design, and you'll have a lot fewer problems down the road. When we look at buildings, generally speaking, I don't know where the fact comes from, but the reality is that the capital cost of a building is about 3% of the cost of a building. So for a lifetime cycle cost of a building, you're looking at operating costs and maintenance costs about 97% in the life of the building. So when you look at upgrading insulation or upgrading windows and that type of thing, you're arguing about 3% of the cost. So if you convince people that if they're going to be holding the building for a while and operating it, their investment should be in a much higher performance building when you're only looking at 3% of the cost.
So David, that actually, I did the pumping system this morning, and I did a calculation. I showed that typically the cost of operating and maintaining a pumping system motor, like drive motor and pump, over the lifetime of the system is only about 3 to 4% of the cost. So exactly the same thing. I think that plays itself out well, and it does reinforce the idea that life cycle costing should always be used in evaluating these situations.
Yeah, we just have to convince the accountants of that. We can take the next slide. So we talk about the installation and the manufacturing style standards. Really, the standards, the building code is, I wouldn't say way behind now. The energy code has certainly come up to reasonable now, but we're still with climate change. We're looking at a lot higher standard of buildings. Again, we're not building buildings for 2020 now. We're building buildings for 2030. And where are we going to be, and what are the energy costs then going to be? So I think people just have short-term memory on things like this, and I've just renovated too many buildings, and I had to go back and increase the insulation, replace windows and things like that, and also access all the mechanical and electrical systems too. So generally when we do buildings, we have accessible systems in bulkheads and accessible walls, shafts and chases and things like that, so that these improvements can happen without a lot of disturbance to the building or having to demolish it, in fact. We can go on to the next slide. So we talked about the contractors and sourcing them. Like I say, I don't need to repeat myself in terms of going to the trades and the house builders. Warranties and that type of thing are hard to find. You have to be careful, and you can say that with the equipment as well. I think anybody's familiar with that who's bought offshore materials and equipment, and you can't get parts for it. And I had one of the first ground source heat pumps in my area, and it was costing about $500 a year just for a part that had to be replaced intermittently, and almost every 2 years it had to be replaced. So the efficiency of the system was gone out the windows, and eventually we had to replace the whole system with something that's more serviceable. Certainly commissioning is a big thing too, in getting it commissioned in the right. I mean, I went to a conference a couple of years ago. I think it's about 25–30% of commissioning finds fault in the design and the installation of systems from their intention. So good commissioning by independent people who are expert in this field when it comes to air balancing and getting the right equipment, the right filters in it, and that type of thing. We've seen, I'm sure all people here have seen valves that are in the wrong way, dampers that are facing the wrong way, louvers, that type of thing that don't function. So these things, again, I mean, commissioning, to get it right in the first place, like I say, you get about 75% chance of having it right.
Yeah, it's interesting. Michelle Perron, who's online, talked last or 2 weeks ago about existing building commissioning, but he talked about the importance of all those things. So you're just reinforcing that even further, David. And yep. I'm just looking on the chat here. Christian Tam from the Municipal Association has just put in a link to a net zero fire hall, so that was built. So there's some good reference to what is being done in the commercial space on net zero.
Yes, and just so you know, there's a recommissioning standard coming out from CSA, and there's a whole section on building envelope recommissioning.
Excellent. That's a good point as well, because the building envelope scientist on the construction site is probably going to save their money and many times over to make sure that these things are inspected. And we certainly ask for blower door testing during construction as well. So before the air barriers and vapor barriers are covered up, we ask for a blower door test, and we have a great opportunity then to seal it up and correct any of the failures that might be in the construction itself. And there are. It's not a perfect system. Buildings are a lot more complicated than cars, and we know the problems that they can have with recalls on cars when they do thousands of the same thing. So certainly engaging all the users at the beginning is a great idea. The staff, patients, families, volunteers, and medical expertise for sure, and follow up with these people too to make sure it's either their concerns have been addressed or why they haven't been addressed. And usually when people listen like that, there's a lot of expertise. We have to listen to the people who are maintaining the buildings, and that's a failure in a lot of the design community as well, because we're not trained to talk to the users. In fact, as architects, we're discouraged from talking to the users. And I think that attitude has to change, because we're all in this together, and if there's a failure, everybody's going to have to pay for it.
A little story for you, David. This is my little handheld thermal camera, about $500 worth of camera, maybe even cheaper today. And I was up in up in Northern Ontario doing a session at an organization up there, and they had a clinic nearby, and we had in our session, we had some people that were users of the facilities. There was even a couple of nurses and medical staff, and there seemed to be a lot of complaints in this clinic about comfort. So we had a 2-day session. So overnight, one person took out this camera and they walked around that facility, and everywhere where they had a complaint about comfort in the facility, and it was a pretty cold night that night, they were able to identify an issue with the building envelope with the thermal camera, which could be remedied pretty quickly, but because they couldn't see it with their eyes, and they would maybe put it down to people, not being happy or something, but there were very real comfort complaints, and the camera was able to nail those things pretty quickly. Just a little story.
I have a question for both Stephen and David on this. I've been approached lately by a company that have the drone infrared, and they claim to quantify, and I don't know exactly how, but quantify savings with the infrared scan, which I thought was not usually accurate or reliable. What do you think about that?
Well, I think it's better than, as has just been said, it's better than people kind of going around and feeling how they are, in the room. So, and I'm brought back to another story. I went to a really good presentation on a building envelope a couple of years ago, and I'll have to go back to the notes on that. But I remember we were in a conference room, and they were talking about the comfort level. Basically, the subject was comfort level, and people think of comfort level. Well, it's just it has to do with the thermostat. So they went to the wall and they looked at the thermostat in this conference room, and they looked at it. I can't remember if it was 68 degrees or 70 degrees, whatever it was. They had scientific equipment in the room, and they brought that in at, let's say, the comfort level of people. First of all, they looked around the room, and people were sitting there in T-shirts in the winter. Other people were sitting with their coats on. Other people had sweaters on, and everybody has their own comfort level. So to try to get the comfort level for everybody is almost impossible. But when they looked at the actual temperature as it was measured with scientific thermostats, it was considerably different from what the wall thermostat was saying. And then they put it up at the ceiling just to see what the ceiling temperature was. And again, it was probably about 5 or 10 degrees more. And on the floor near the door, it was about 6 degrees lower. So, I mean, if people talk about comfort level and they look at the thermostat that's 4 feet above floor level, and they say, well, that's the comfort level. Let's turn up the thermostat, we're cold, or let's turn it down because we're too hot. And comfort is only, the temperature is only one thing, and it's not a very good thing to measure temperature. We can think of the humidity, of course. We can think of the drafts, with airs. That's why I'm a big proponent of radiant heating systems and ventilation systems that provide ventilation air, but not cold air, because even in the summer, cold air blowing at you just freezes you out. That's why a lot of people don't like air conditioning, because it's just blowing cold air at you. So we have to look at segregated systems, I think, for heating, ventilation, and air conditioning. Whereas now with rooftop units, the same duct provides the heating, the ventilation, and the air conditioning, and they all have different characteristics. So I think we have to be careful with the design and some of these things as well. So take a look at the comfort level, and like I say, it's a lot more sophisticated than just an adjustment of a temperature, which is probably not that scientific in the first place anyway.
And going back to Michelle's, and when we started there about the drone thing, my comment about that is that the use of thermography to detect and quantify heat loss is possible, but it really requires a lot of skill in terms of knowledge of the materials that you're actually looking at, because the emissivity of a surface, the ability of it to radiate, right, as a function of its temperature, can vary dramatically. Like aluminum has a very low emissivity, whereas a lot of other materials are high emissivity, but you can fool a thermal camera very quickly, and you can be looking at the sky and not actually at the building. So with the right skill and training, I think it can be done, but it's not something that I would, it needs a lot of care.
Yeah, it's only as good as the operator, I guess, is kind of what you're saying too, right? The experience.
And this is another question for you, David. With the COVID and pandemic, we've been told that minimum humidity should be about 40%. Definitely in healthcare, that's if the humidifier can keep up. Do you think the building envelopes that most of those buildings have can take 40% relative humidity in the winter?
I think it's going to be really, really hard to do. It's going to take its toll on the building envelope itself, the insulation and finishes and that as well, because 40% is, yeah, I mean, ideally, you want to, for health, you want a humidity level of in excess of 60%. So 40% is really, really hard to accomplish. I think it's going to really it's going to basically throw the mechanical systems out, just trying to get to that. I think the intent of doing individual filtering is going to be a lot more effective over the shorter term before because we're not going to go and replace all the mechanical systems in a building, across the board. So I think there are easier ways to control COVID. I've been to a couple of seminars on that, and it seems that the HEPA filters on a localized basis.
A lot of specialists say now, not just for COVID, that 40% should be in healthcare setting, and actually they say everywhere, 40% for any kind of viruses, bacteria should be the health minimum in buildings for humidification, which I think is not possible in most buildings, but just in terms of building envelope, I would assume most envelope cannot take that.
Yeah, with healthcare facilities, we typically with CSA standards in those areas where we have patient care, especially intensive patient care going on, we've always looked at a range of 40 to 60%.
Mm-hmm. Yeah, and again, I mean, this is probably a renewed new design. If it has to be 40%, if that's what the neurologists are saying, then I think we're going to have to go through and look at the buildings and where we can accomplish that.
Yeah, I think the ideal level is 50%, so they make it a range of 40 to 60. It just helps people shake off a virus like COVID.
Mm-hmm. Yeah. And I think COVID is one thing, but there's a lot of other things with mold and other contaminants in the air as well, particulates that
Right.
can also be moved around and complicate things as well.
Right.
Okay, can we move on? I think this is really just talking about how things have been in the past. We're kind of at the 20th century now, where we've got lots of mechanical and electrical systems all over the place. We're conditioning every space. In the 21st century, we're looking to more passive systems, and this is really an ad for the passive house systems that are. The next slide shows you what the criteria are for the passive house, basically. So you're looking at more passive systems with HRVs, ERVs, recovering air. So you're looking at heat recovery, higher ventilation rates for sure now. And I don't know what they're bringing up now with the passive buildings, but certainly with COVID, they're probably going to have to adjust some of their criteria here. But these are the basic criteria as far as ventilation is concerned, glazing, and all of this again is done on their modeling system. Next slide. So again, the benefits of good building envelopes is certainly first and foremost is a healthier resident environment, and along with that is the staff environment too that's affected by that as well. Certainly climate change mitigation, carbon footprint reduction, longer life and sound separation too. We find with triple glazing particularly, you don't need to look at the same sound separation. The buildings are very, very quiet. Next slide. Other benefits certainly are cleanliness and personal safety, natural lighting, certainly with better windows. And this is a proven biophilic thing when they've looked at hospitals where they've had looking at a tree outside as opposed to a wall of brick or something like that. The healing and the medical treatments are much more supported with that, with reduction in infections and that type of thing. So I think we have to look at things like biophilia as an option to be in the mix. Next slide. Challenges to building envelope. Certainly we talked about uncertain costs. That's something, especially when you're getting into older buildings, you get escalating costs and difficulty finding contractors even do that type of thing, and certainly construction conditions that are unforeseen. It's difficult to separate out the energy upgrades from other work if it's part of another project. And we talked about finding experienced, competent people. Next slide. There can be a lot of challenges. Limited sources for specialized innovative materials and equipment, and limited competition, and certainly for approvals on some of these people as well. So certainly we're looking at, we can't sole source things, but it's going to improve the more that these buildings are more commonplace. Next slide. As I mentioned before, it's difficult to access insulation and barriers behind finishes. So if we had finishes that could be removed more readily, and then we can improve some of these things at some point down the road. Construction access, particularly in the healthcare field, is always an issue, and disruption, noise, and dust, and infection control. I don't know how we're going to be able to do that. I've done a number of hospice cares, and those buildings can just never close down. So doing any improvements after occupancy is almost impossible. Is there any potential damage to existing services where you're going in and removing things? And certainly a time schedule, drawn out schedules and things like that for these projects. Next slide. So the resources, I talked about RDH. You can Google them, and BSC and other Building Sciences Corporation. Roofing consultants, I think everybody has their area of competent roofing consultants, and there's associations. For designated substances reports, again, it's a localized thing. Some people are all over the place, and occupational health, ALCO is another company we've used for occupational health that has some understanding of what buildings are made like. So resources and credits are LEED and well building, which is very common now, net zero, passive house, building biology, and biofuel. You can just Google these to find out all their contacts and the people that are licensed or experienced in these fields. So if you want sources, that's the place to go. Next slide.
Yeah, I thank you for teaching me a new word today, David, biophilia.
It's an amazing field. Yeah, it's pretty deep, actually. But it brings a lot of what we're talking about together, together with the health professionals. It has a lot to do with healthcare and education.
I'll be Googling that one tonight.
Yeah.
Have fun. So this is the end. I've been a lot of great questions through it, and I thank everybody for that. So we're open to some dialogue, I guess, in whatever time's available.
This is Brent
Any
Godbout.
last?
Can you hear me?
Yeah.
This is Brent Godbout. I used to do just more of a few comments. I used to do infrared scans, previous job that I did, and we never did get into trying to calculate the actual energy savings, like I think it was Michelle was indicating with the drone company. But a couple things that they were, I think someone was asking about reputable companies. Make sure you ask them, what time of day they're going to come and do that. I think Stephen already touched upon that. You got to come. Best time is either on a cloudy day or at nighttime, obviously when there's a good temperature difference between the outside and the inside of the building. And also another good time is to do it when you do the blower door, just because you're going to have a good pressure differential, which will make all of the spots show up that much more. Another one I noticed was there was a picture, I think, David, in your slide of a roof that had a rock. It was a rock roof. If you're looking for, yeah, if you're looking for leaks through your roof, water leaks, you can't do it on those roofs, obviously, because you got to be able to see the roof. The best roofs are if you have like I'm calling it the rubber roof membrane. I don't know if that's the correct word, but you can really see it on those. The water just pools where the leak is. I think that white roof, is that a rubber material?
I think it's an EPDM.
Okay, either way, with the water pooling underneath the surface where the leak is, during the day it just heats up from the sun hitting it, and then if you go scan it at nighttime, that water holds its heat, so it just shows up nice and clear on an infrared camera. Just a couple comments more than anything.
And by the way, if you don't,
roofs, have you tried infrared surveys of ballasted roofs to find out where the issue is?
I have not done that myself, no. And this was 10 years ago when I did this. I haven't done it in a while.
Sorry, I was just gonna say, if you don't do a blower door test, commercial building, when you do recommissioning, we do have a pressurization test using the building's HVAC system, which can be useful when you do your infrared scan because it does pressurize the building using its own HVAC system. I can provide JJ with the procedure for that functional test if anyone's interested.
Yeah, I can really endorse the importance of having good pressure differential one way or the other across a building. I once ran into a building that we were doing thermography on. This was like 30 years ago. And the old thermography equipment back then, I had to carry like a liquid nitrogen tank in order to cool my camera. So a lot more complicated than it is today. In any event, we were out on a very windy day on a building that they had 3 boilers in. It was a new building, recently built. They couldn't hold it on a cold day in the winter with 3 boilers, even though originally it was designed to work with 1 and 2, second as a backup. The third was for a new building they were going to build next door. Anyway, we went up and we looked at the windward side of the building, and it was all one color. We went to the other side, and sure enough, around every place where the roof and the wall and other elements interface, and where there was supposed to be membranes and weather stripping and gasketing in there, it was all missing, and you could just see the outline of the building as the hot air was being blown through the building from the other side. That was on the leeward side. So yeah, the pressure differential just makes some of this stuff just pop out in thermography.
And I think with that, somebody talked about a 12-story building with that and buildings, I guess, above about 4 stories. The chimney effect is also, the stack effect in the building is quite substantial as well.
Yeah, and they were able to actually find the neutral pressure point in the building, like where you go, right? So yeah, I think you know the guy that did that test.
All right. Any last minute questions for David? If not, I'd like to thank you, David, for a very insightful presentation. It's well done. Thanks.
Yeah, and timing was perfect. It was great.
Absolutely.
And I want to thank everybody for your questions. I've learned a lot too.
Yeah, and we do have your contact information, so thank you for that as well. You never know, there'll be people with some questions that will come up later down the road, and maybe they can look to you for some answers. Thanks for that.
Okay, thank you very much. Bye.
All right, so with that, I think we should take a 5-minute break and come back. And I've got 2:32 on the computer right now. Why don't we come back at 2:37 and we'll get into renewables.
Sounds good. See you in 5, folks.